Had your lunch? How was it? Huh? Same menu. No, menu. Same curry they repeated. No, quality is fine, but I requested them to change the curries. So no change. So okay, we will. There are some biscuits, you can have it. Okay, nothing should be left from here. Everything is. Yeah, you have to finish. Otherwise, we don't allow you to go. So, good afternoon, everyone. Half session over, half session left. With us, Professor P. Veeramani from IIT Madras, and he will have two sessions. In session 1, he will speak about fixed point theorems for contractive type mappings and cyclic contraction mappings. The second one is the role of multi-valued fixed point theorems in the study of existence of Nash equilibrium points. So these are the two titles. One is related to proximity points, okay, cyclic maps, and other one the Nash equilibrium problem. So as Professor rightly said, yesterday he was talking about, in mathematics there is no Nobel, so it is unjustified with us. We do lot of work, but we have no Nobel Prize. Is there any conspiracy, sir? You have any news for this?
Nobel Prize is there.
No, Abel I know, Abel I know, but Nobel I don't know.
Yeah, maybe.
So, field medal is there by International Mathematical Union. Those who are willing to attend Philadelphia 2026 ICM, you can apply, and those who are who have obtained their PhD after 2018, they can also they can apply for travel grant, ICM travel grant. I don't know whether they have extended or not. 20th of November was the last date, okay, what I applied. So you please, those who are, okay, Rashmi is there or not? No. So my PhD scholar, she got Brazil ICM travel grant to attend ICM at Brazil. I think it is 2018 maybe, 16 or 18. So you can also apply for the same. After some time, for Nepal, Professor Jha is the main person. Okay. So because Nepal is also included and they have given some special privileges for ICM. So I thought Jha is there, some people are here. When they see Murthy, they will provide me the travel grant, but they have not provided. So for Indians, there is another also, that is the NBHM's travel grant. Most probably you can get the time within 6 months. I think it is possible to get the PhD, so you can apply for this. You, Pushpalata Sahu, all of them can apply for that grant. NBHM will announce once again, but they need very good SCI papers. SCI is mandatory, okay. So you can apply. Age restriction is there. I think that is 30, below 30 or 28 years. So you check your age also. So now with us, Professor Veeramani, he will start with the contraction type mappings. And as professors always talk about the Billy Rhodes, you can, I think those who are from the fixed point theory, 1977 paper, Proceedings of American Mathematical Society, that is 225 definitions, right sir? Actually it is 25,
Yeah,
but they are numbers they are comparison they made it comparison of various types of mappings. That is the title of the paper, and he revisited also in contemporary, and several times he has written. So you can refer those papers. So I request Professor Veermani to continue his lecture today. Thank you,
thanks
Professor.
Again, Professor Murthy. So welcome back. Maybe first half an hour we will spend whatever we left yesterday. Especially we just started Jones lemma and what is called reflexive Banach spaces. These ideas we will be using tomorrow when we discuss fixed point theorems. Mainly today also Professor Perende has discussed some results related to non-expansive map and there are other type of non-expansive map. Will prove the main importance theorem proved by Prouder, Kirk and the same time in 1965. That will give the proof so that you will know the how we use the concept of little advanced compared to contraction. So that we will recall what is essentially compact. Compact in some other topology induced by the norm, that we call it weakly compact, that we need, that we will recall. And then Jones lemma is very important. Okay, before that yesterday any questions? If you don't ask, I will ask. So then you will have to answer. Any questions? Any doubt also okay. Whatever we discussed yesterday, if you have some doubt, you tried and you could not, then you can ask. Some exercise, we left us some small things we did not discuss, we left it as an exercise, correct? For example, okay, this we discussed. Again quickly, F from close interval a comma b to close interval a comma b, a less than b is a continuous function, continuous, then what is the conclusion? It has at least one fixed point. So then we used what we need is continuous image of a connected set is connected. Other is what we know as a consequence, what we call intermediate value theorem. For that what we took, define another map G from close interval a comma b to R as G of x equal to either x minus f of x or fx minus x for all x in the domain. To make it simple, yesterday we took it close interval 0, 1. See, many times, sometimes actually the beginning, students may feel easy to fill close 0, 1 inside close interval a comma b, but proof is exactly same. So then what we did, our aim is to find at least one x such that fx equal to x. That x may be a or b or in between, it may be anywhere. Suppose, that's how we took case 1. Suppose f of a equal to a, then we are through. F of b equal to b, we are through. Otherwise what it means, suppose, that means we are assuming f of a not equal to a, f of b not equal to b. What does it mean? Where is f of a? It is a, see, what is the importance of the self map also we should realize. See here, A, forget about now, this closed interval AB to here. What is f of a not equal to a? And where f of a belongs to? F of a belongs to closed interval a comma b. And f of a not equal to a means f of a is strictly greater than a. Somewhere it may be, if you are writing doesn't mean that it is less than b. Anywhere between a and here anything right side. That means what? What is f of a minus a? F of a. So this is positive. And f of, sorry, this is whatever g of a, correct? G of a equal to this. And what is f of b minus b? Again, b not equal, f of a not equal to this. This cannot go to right side. Similarly, your f of a cannot go to left side. That is self map. Image of each x in the domain, fx again in the same domain. So, then not equal hence this. Now what happens? F of b less than b. So this is at one, that's what this is our map G. At one point it is negative, at another point positive, 0 is in between. Hence we get an x in the domain so that gx equal to 0. Gx means fx minus x, 0 means fx equal to x. That's why sometimes given to prove result, how we get the motivation is through examples. See the example, using the example we'll get an idea whether we can do this for a general. Even as I told Prower fixed point theorem, first proved for unit ball, then for any compact convex subset of finite dimensional non-linear space. Then further proved for infinite dimensional. Even not only each is very important. Later Kakutani proved, that will come in the next lecture, proved for multi-valued map. Again, what is called Tikhonov. He proved it for, some of you may be familiar or may not be familiar, what is called topological vector space. If it is a compact convex subset of a topological vector space and f from k to k continuous map, yes, it has a fixed point. Even that has been further generalized for multi-valued maps and many other directions. Okay? Okay, this is one thing. Any other, like this symbol, any other doubt you have? Whatever we discussed. Any doubt? Okay. So first I will start Jones lemma. You remember yesterday we just recalled to use Jones lemma. What are the first? We have a non-empty set. Our set is non-empty. Just okay. We start with a non-empty set, which we call it capital X. Capital X here, non-empty set. And we have a relation where, what do you mean by relation? Relation is a subset of which one? X cross X. So relation, if you want, call it R. We have a relation, it is a subset of X cross X. Meaning is, we don't mean proper subset. It may be set inclusion. Whenever we mean subset, including we use with this as, understanding. A subset of A means X in A imply X in the other set also. Then this is a relation. That's what we know that. Even we can say that 1, 2, 2, 3 is a subset of R cross R. It is a relation on where R. It is enough to have a subset. So what type of relation? Is it reflexive?
Symmetry transitive.
No. Question is whether this relation defined this way. See now, whether this relation is reflexive.
Transitive.
No, question is whether it is reflexive or not. We did not, I do not know what is transitive, not defined. Right now, okay, reflexive also we are not defined. What is reflexive? Each element in the domain. Domain is what? R, set of real number. Each x is related to itself. Even for example, any real number. 1, 0, 2, root 2, whatever may be, it is not related to itself. Here what do you mean by 1, 2 belongs to R? Here this is our R. 1, 2 belongs to R. Then we write 1 less than or equal to 2. Okay? Here, alright? Any doubt? Okay. So now I will include just for some, you see the y, comma 100 also there in the set R. Now 1 comma other way, right? 100 comma 1. 100 comma 1 belongs to R imply what we write under this notation? 100 is less than or equal to 1. This is not our usual relation on R. The relation which we have defined the way 100 is less than or equal to 1. So instead of writing order per xy belongs to R, we write x less than or equal to y. Sometimes they write different notation, they write x related to y. This is what we write in place of that this. Or some other symbol also we write. In fact, using the symbol less than or equal to will give later to define upper bound, lower bound, least upper bound, greater, everything will become easier. Like in R we are familiar, the set of real numbers with our usual less than or equal to relation. Okay, now we have set x is a non-empty set, less than or equal to is a relation on x. What is less than or equal to mean? That R xy belongs to x related to y, meaning is x less than or equal to y. Okay, R is there. Order per xy belongs to R means R, the set R, subset of x cross x. Then we say that x less than or equal to y. When we say reflexive, for each x in capital X is less than or equal to x. That means x is related to x for every element. Then only we say it is reflexive. Transitive means it is conditional. Reflexivity no condition. Whatever may be the x should be less than or equal to x. Whatever may be the real number, x less than or equal to x. So like that. Now, transitive, conditional. Suppose x, y belongs to the domain x related to y. That means x less than or equal to y and y less than or equal to z, then x less than or equal to z. Conditional statement. Transitive. Next is symmetry. Yes, okay, what do you mean by symmetry? Like usual. If, again conditional. If x related to y, then y related to x. That is symmetry. Partial order, we don't like symmetry. Where y equal to x, mean x equal to y, then x related to y, x less than or equal to x, that is comes from reflexive. Otherwise you don't want symmetry. In a strong sense, we are not saying not symmetry. The relation is not symmetry means what? There exists a pair xy such that x related to y, but y is not related to x. But what is anti-symmetry? Anti-symmetry is same as not symmetry? No. Very good. That is, here again, if x related to y and y related to x, that means symmetry between x and y. Then what cannot happen? They cannot be different. That's what x related to y. That's why similar to R we compare x less than or equal to y less than or equal to x imply x equal to y. That's what we call it anti-symmetry, essentially again like against symmetry, even for one pair when they are distinct. Then such a set we call it a set capital X. We have set capital X and a relation, that relation R, then we understand that xy belongs to R means we write x less than or equal to y. So we just write that x less than or equal to x is our set. The relation, using this we got this. These relations satisfy these three conditions: reflexive, anti-symmetry and transitive. Then the set x together with that relation is called a partially ordered set. This is also important. Later I think Professor Garande is going to discuss, or Professor Murthy, partially ordered metric spaces, or there they will define on a metric space some partial order relation, then using that they will discuss some fixed point theorem. Here our interest is, we have a partial order set. Now see, because of this relation notation, when we say an element, say x naught belongs to a, naturally the whole world is now, we do not know anything about other than x. X naught belongs to x. We have a set like a non-empty in salt. We write this as a partially ordered set, just we write pro set. Capital A non-empty subset of x. Then x naught belongs to capital X is called or said to be on, this I am writing for upper bound, if and only if, we all know what is the condition. When we say x naught is an upper bound for what? Upper bound for the set A, if and only if, conditional again, x belongs to A imply x less than or equal to x naught, that's all. That's what similar to, if you use some other notation, you can use like R, then what we will have XR, y or x naught, like that, it will not be getting that idea immediately. Now upper bound means we know like in R, x less than or equal to x naught for all x in the domain, here our for all x in the set A, then that x naught is called an upper bound for A. Again upper bound need not be like in R, need not be in the set A. It may be in A or it may not be in A. So that is second condition. Then everything, then we have here again C, we take non-empty set, subset of x. When we say this is a chain or a totally ordered set, again see, from both we get the idea. Totally ordered means you give any why we call it partially ordered? Like we saw the example, 1, 2, 2, 3, where 4 and 5 are related. 4, 5 is not in our R. That means we cannot say 4 related to 5 or they are not related, but they are in the capital X. I mean, that we have to check, that was not a partially ordered set, the given example. So our set here, it is a partially ordered set. Okay. Then when we say it is a totally ordered set, total order set means what? XY belongs to that set imply either XY order for XY belongs to our relation. So in our notation, X less than or equal to Y or Y less than or equal to X or equal already there. The X less equal to X is there. So we don't imply X less than or equal to Y or Y less than or equal to X. But can both happen? That's what, that can happen only X equal to Y. That means what? Suppose X not equal to Y, then only, like that case we write strictly less than. Anyway, we don't use strictly less than right now. It's clear? Then such a set we call it a chain or
Trichotomy code.
pardon?
Trichotomy. This is called.
Yeah, okay. There in real analysis, whatever we have, either for given any element, either x equal to y or x less than y, and that here we just here on any partial order set, not just in R. So we'll use the term chain. Chain or total order set, the name. So what are the things we have here? Partial order set, and if we have a non-empty subset, we know when an element from X is an upper bound and when a set is totally ordered. So this we know. Another somewhat, I mean for a beginner, not that immediately you will get is what is called a maximal element. Similarly we can define minimal element. See, yesterday we gave example. Maximal element. It is not maximum. Maximal, even in R or this, we don't say it is maximum element, maximal element. So we use that. For that we do not require any subset. X is partial order set. X naught belongs to capital X is said to be a maximal element of capital X. Definition means either you write if or if and only if same. When we say X naught is maximal element, that's at the topper in mathematics, topper in physics, topper in chemistry, all are maximal element. But topper in maths not related to topper in physics like that. So among the related people he is the best. If they are so, that's why we say if and only if X belongs to X, X naught is smaller. It is like X naught is inferior to X. So marks obtained by the X naught and X less than or equal to X means that should they are equal, no problem. So other only this topper means X naught less than or equal to X imply
X not equal to X.
X not equal to
This implies X not equal to X.
X not equal to X. x naught not equal to x.
x0 equal to x.
What?
X naught. This condition implies x not equal to x, then x naught is called maximal element.
No, this imply, see this is maximal. See, maths one student topper is got 90 marks. Suppose somebody, we can say some other x naught is less than or equal to x. That means what? X should have got more marks than x naught, either equal or more. But only one topper means that such thing cannot happen. That's what we say. X naught less than or equal to x imply.
X not equal to x.
No, what is the natural thing? Can anyone else, topper got 90 in maths. Can there exist another topper with the same 90? We assume that they are all distinct. No two different students will get same marks. We will assume just for simplicity. So they are not equal, but x naught less than or equal to x means what? Not equal but strictly less than. Then the marks obtained by x is more, but we call it x naught is maximal, we want to call. So such things should not happen. That means what? What is the relation between x naught and x? X naught should be x naught is not related to any two elements in mass are related. One topper in mass not related to topper in physics. If they are from they are already related, given they are related. It is given that x naught in capital X, when we call x naught is a maximal element mean, suppose conditional, if there exists an x such that x naught less than or equal to x, whether that is possible. Possible or not? MSc somebody. See, x naught less than or equal to x means x is superior.
X is superior, yes.
Yeah, but maximal means
Maximum.
above him nobody is there. See, that's what we gave the lattice diagram sometime called, if you have mass like this. One student here, the topper is here, above him nobody will be there. Some other physics, here and here not, they are not related. So he is topper, above him anybody will be there? Nobody will be there. That means what? X naught less than or equal to x should imply what is the relation between x and x naught? They are correct. Equal, very good. X equal to x naught. I mean x, okay. So x in x naught less than or equal to x imply that x equal to so x equal to x naught, no contradiction. They are equal mean reflexive is there. Okay? That's why this is somewhat you have to little spend some time. If you are listening first time, maximal element, because some of you might have not seen Jones lemma, things like that. It will. So there is any doubt? Right. I mean.
For some x belongs to x.
No. Conditional.
A condition.
Suppose there exists x, such that this condition is satisfied. Whether there exists at least one x equal to x naught. X naught is already less than or equal to x naught. Other than that, there will not, x naught less than or equal to x should imply x equal to x naught. It's clear? So this we call it maximal element. Maximal element may be more than one. For a partially ordered set, That's a vector space, all of you studied, no? Vector space. Suppose R2. Can you tell what is a basis for R2? 1001. It is a basis. Any other basis? 1, 2, 2, 3, any number of, any linearly independent set containing 2 elements. They are all maximal linearly independent set in that set. What, at least you heard about maximal linearly independent set? A is a linearly independent set. Capital B is a not linearly independent set containing something. Okay, that's what we are going to see. These are all, every vector space has a basis, non-zero vector space. Zero vector space also has a basis. Some books they may not like empty set, they don't like me. Empty set also a basis for span of empty set. Span means what? Span of a set A means it is a, correct, it is a subspace, smallest subspace containing span A, containing A. What is the smallest subspace containing empty set is single, that zero element alone. That element, but that is not linear. So empty set is linearly independent in that sense. Span of empty set is singleton 0. Hence, that basis containing empty set basis. How many elements are there? No element means 0 element. That's why the 0 space contain, it has a basis, dimension is 0. That's why 0 space dimension 1, one non-zero element means dimension will be greater than or equal to 1. That's why there also we will prove in finite dimensional vector space, we can start with any non-zero element. Suppose x1, consider span of x1. If span of x1 equal to the whole vector space V means span x1 equal to whole vector space V, x1 is non-zero means linearly independent, then it is a basis, dimension is 1. Suppose span of x1 is not equal means proper subset, then we will get an x2 in V not in span of x1. x2 in V, x2 not in span of x1. Then x1, x2 will become, we can easily prove that linearly independent. Then x1, x2 linearly independent, consider span of x1, x2. That may be equal to V if it is equal to V, x1, x2 basis, otherwise continue still finite we can go. But infinite dimensional we cannot do that, so for that we need Jones lemma. Using Jones lemma we can prove that, start with any linearly independent set inclusion. A, we have a collection of linearly independent set containing one particular linearly independent set, then A subset of B means A less than or equal to B, like that. Then we can prove using Jones lemma maximal linearly independent set exists, that will be our basis. But our main aim here is fixed point theorem. So this exercise, use Jones lemma to prove that every vector space has a basis. Okay. Now what is Jones lemma? We have a non-empty set, then we have a partially ordered set, then take any chain, you can assume non-empty chain, any chain, suppose every chain, we keep going, we cannot go beyond the root, every chain should have an upper bound, once going like that it should have an upper bound. If every chain has an upper bound, then it will have at least one maximal element, at least one maximal element. That is what Jones lemma. That is we call Jones lemma. You want any hint to prove vector space as a basis? You want hint, I will give, otherwise you try yourself. Which way you want? Pardon?
Can be done.
Okay, very good. Okay. Now, in fixed point theory, how we are going to use, just I will indicate because I stated, tomorrow we will discuss that. In fixed point theory, some type of compact set we will assume that X is a non-linear space or even assume Banach space, capital K, non-empty, it is even assumed that compact convex subset of X. In fact, what we need is, instead of compact, something called weakly compact we will assume. That I will explain. K compact convex, T is a norm from K to K. That means T of K, subset of K. X belongs to K, is Tx belongs to K. We have this condition. It is called a self map. Then our aim is, there exists to prove, or aim or to prove, there exists X in K such that Tx equal to X. This we want to prove. Can you think of some minimal set similar to maximal set? If we have a partial order set, suppose every chain has is of upper bound, lower bound. If every chain has a lower bound, then it will have a minimal element. Can you think of a minimal set having this property? K is a subset of our Banach space. Even Banach space or metric space set doesn't matter. It is any set even, okay. Later in the proof we need all those things. Can you get a smallest minimal set? What is the condition? Say, let us say F is a minimal set. That means what type of set you have? So that X belongs to F imply Tx belongs to F. X belongs to F, F is subset of K. See, we want that, this we will call it script F, set of all F subset of K. What is important is empty set should not come. Some other condition later we will assume. This. Whether this is going to be our partial order set. Script F. This is non-empty. This collection script A. Script F is a collection of subsets of K. An element F belongs to K means F should be non-empty and it is invariant. I mean the T restricted to F is invariant, meaning X belongs to F imply Tx also belongs to F. Can you give, then what is our aim? What is our goal? We want to find an X such that Tx equal to X. So what should be that F?
Single set having
So we have to prove that use Jones lemma to get a minimal element. Then use some other additional condition. The minimal element alone will not be sufficient. Something else in non-expansive, proved by Prouder, Coke and Kirk in 1965. They first, in fact, Prouder proved in 65 for a Hilbert space, assuming that K is a closed, bounded, convex subset of a Hilbert space, T from K to K non-expansive. Non-expansive are explained in the morning also. That means norm of Tx minus Ty less than or equal to norm x minus y. for all xy in the domain. Okay. Then under this condition, K closed bounded convex subset of a Hilbert space, T non-expansive map, then there exists x in K such that Tx equal to x. That proved or proved. Then at the same year he improved his own result. That is something called what is uniformly convex. For example, finite dimensional uniformly convex is simple to, you have here, see what is in R2? Have you seen the square or rhombus like this? What is this thing? Units R2, what are the norms you are familiar? R power 2, Euclidean plane. Order pair x1, x2 or xy. Order pair x comma y. What is the Euclidean? Another name for Euclidean is Pythagoras. In fact, how you get the idea of the usual distances, use Pythagoras theorem. I mean, just if you see that symbol quickly, we want spend. Suppose this order pair xy, we want to define this is our distance between, in this case x0 will assume. I mean, we call it xy like this. Then this distance is y minus x. 0 will be anywhere else. Correct? No. Sorry. 2 point, we will assume that this is 0, 0 or this is xy. Then this distance will be x. This will be y and this will be root of x. That comes from Pythagoras theorem. Similarly, any instead of this some other x, I mean this distance is the plus this, that's what the root of that what is so called Euclidean metric. That metric you are familiar. Or norm of order pair xy equal to positive root of x squared plus y square. What is L2? This we call it L2 norm. What is L1? Norm of order pair xy, suffix 1 to distinguish, equal to norm x plus norm y. Yeah, norm x plus norm y. And L infinity norm or maximum, that is maximum of mod x comma mod y. There the unit ball all like this, say square L infinity or L1 rhombus type. What is there? The problem is, if your unit sphere is like this, square type, that means x is here, y is here, norm x equal to 1, norm y equal to 1, x not equal to y also, norm of x plus y also 1. Such things should not happen in a finite dimensional non-linear pair. If it happens, that means norm x equal to 1, norm y equal to 1, x not equal to y, in fact the midpoint, norm x plus y by 2, strictly less than 1. That's what our unit sphere, like our usual Euclidean norm, root of x center at 0 radius 1. Here any point x here, x means order pair, x1, x2. If you want to call it x1, x2. Another point here, then midpoint where it will be? Midpoint will be strictly less than 1. Not only midpoint, if you take any point in between, later we will see for equivalent other than the end point. Such spaces, finite dimensional, this will be equivalent to uniformly convex. We will define later. That is called uniformly convex Banach space. I mean non-linear space also, uniformly convex Banach space is more important. That implies it is a reflexive Banach space like that. but like L1, L infinity will not have this property, even finite dimensional, because you take the point on the norm x equal to 1, norm y equal to 1, some x not equal to y, still it can happen that midpoint also on the unit sphere. So they are not strictly convex. This happen in a uniform way, that is called uniformly convex. We will discuss if necessary. Otherwise, what is important is, this prouder, then you can prove that every Hilbert space will have this property. That means norm x equal to 1, norm y equal to 1. Suppose not only that, what is called parallelogram law. So use parallelogram law to prove this. We can say, in fact, prove more for given epsilon, we can find a delta, so that norm x less equal to 1 or less than or equal to 1 doesn't matter. Norm x less than or equal to 1, norm y less than or equal to 1, distance between xy is at least greater than or equal to epsilon. Then the midpoint, norm x plus y by 2 less than or equal to 1 minus delta. That means that is norm x plus y by 2 or strictly less than 1. Such concept is called uniformly convex. So later proved, because every Hilbert space is uniformly convex Banach space, Prouder extended the same result to uniformly convex Banach space. Like LP space, little LP, 1 less than p less than infinity. When it will be Hilbert space? Only when LP space is done somewhere, little LP, if not capital LP. Little LP, each element set of all sequences, assume that 1 less than p less than infinity. X in LP means summation n1 to infinity mod xn power p less than infinity. That series converges. P summable we call it. Then there we define naturally a norm. Norm, that's all. Norm of x is summation n1 to infinity mod xn power p whole power 1 by p. That norm. That is a Banach space. That will be uniformly convex, but not a Hilbert space when p not equal to 2. 1 less than p less than infinity. It is to L1 and L infinity, they are not even strictly convex. Okay. That's a Prouder, and same time another mathematical Cope key proof. Again around the same year, what is one Kirk is a, like Professor Perendi also pointed out, he has contributed a lot of things in fixed point theory. He proved it for using closed bounded convex subset of a uniformly convex Banach space, mean it is reflexive, then closed bounded convex is what is called compact in the weak topology. That's what weakly compact. Then use Jones lemma to get a minimal element. Then what we have to prove? That minimal element, using that we have to get a fixed point. Then prove that minimal set is singleton. For that we used a concept called normal structure. That we will discuss tomorrow. That was introduced by 1948. Yeah, introduced by, they proved for a for a family of common fixed point for isometry map. Isometry means norm of Tx minus Ty equal to norm y. Okay, that we will see. Only just I will tell what is reflexive, then we go to you have a Banach space or non-linear space. What is called dual space? X non-linear space. Non-linear space, no need of giving the definition. We have a vector space, we will assume over R, real vector space. Length of the vector, x goes to norm x means that distance between 0 vector and x. That's why we call it length of the vector. Then as usual, length should not be non-negative, it should not be negative, greater than or equal to 0, equal to 0 if and only if this x 0, then norm of x plus y less than or equal to norm x plus norm y, the norm of this additional, norm of alpha x equal to mod alpha time norm x, homogeneous whatever. Then d of xy, if we define norm x minus y, x non-linear space, define a metric on x as d of xy equal to norm x minus y. You can easily verify that that is a metric space. Then complete mean every Cauchy sequence in x with respect to this metric converges. Then we call it complete. Metric space mean we know everything, open set, closed set, compact, everything is there. Okay. So what is the dual space? Even vector space you have done. Dual space here, their continuity is not there. Why continuity is not there in a vector space?
Metric is not there.
Metric is not there, no topology is not there. Something approaches. Okay, a vector approaches another vector, we don't have the concept. Here topology, at least metric, it approaches. So here continuous linear functional. Here what is x prime mean? We will assume that vector space overall set of all F, because our vector space is overall, such that F is continuous, and because non-linear, continuous and linear. What is nice property here? For a linear map, continuous, how many points will have to verify? 1 point. It is continuous, linear important, not linear means it is not enough just to take 1 point, it is continuous everywhere. So continuously, so there it is easy to verify. It's a continuous and linear, set of all continuous linear map on x prime. Okay. Then we can define a norm on this space. This also we can be norm of f equal to supremum of mod fx, such that norm x less than or equal to 1, or supremum of mod fx by norm x, x not equal to 0, all those. Okay, that will not spend time. There is a norm on the dual space. It is also a, in fact, x is non-linear space, but x prime is always vector space. We can define f function, g function, f plus g alpha f. It is also a someone Banach space. Only teacher will have to tell, students should also. Okay, it will become a Banach space. Okay, so we have this. Now this metric on x will induce a topology. That means x is non-linear space means it is a metric space. Then we can define a open set. A is an open set means x belongs to A means x is an interior point. Interior point means for each x there exists at least one radius, so that the ball center at x radius r is contained in A. So open set we know, then complement we know, closed set, all those things we know. So here there is we have the topology, which we call it topology induced by the norm. That is the usual topology. Another topology which we call it t tau omega tau w, whatever tau omega we call it. This is, we are going to call, it is the smallest topology on x having some nice property. What is that property? See now, we have this is x. F belongs to x dash imply f is linear and f from where to where continuous? X to x with respect to this norm to r. What is r? The usual mod xy is distance between xy is usual metric on R, d of xy mod x minus y. There